the example we were talking about was that of Ramsey numbers. And we defined the Ramsey number for two parameters R and B. And we said that this is the smallest number n, such that if you take a complete graph with n vertices and color all of its edges with either red or blue, then you will either have R red vertices such that all the edges between them are red, or you will have B vertices such that all the edges between them are blue. And we talked about the idea that these numbers actually exist. And let me just do that proof. So I want to show that I have this inequality. The Ramsey number on parameters R and B is at most the Ramsey number on parameters R minus 1 and B plus the Ramsey number on parameters R and B minus 1. Okay? So let's call this one N1. Let's call this one N2. And let's say that the sum is just N. So I consider a complete graph on N vertices. Okay? So I'm not going to draw the whole graph, but let's say I have a complete graph on N vertices. And let's say that I take vertex number 1. Now, some of the vertices are connected to this vertex by a blue edge, and some of them are connected by a red edge. So let's say these are the vertices that are connected with blue edges. Vertex number 1. And let's say these are the vertices that are connected by a red edge. Okay. So now just look at these vertices here, and let's just take the graph that is limited to these vertices. Okay. If the number of vertices that are connected to vertex 1 with red edges is at least n1, so if the number of vertices here is greater than or equal to n1, what do I know? I know that inductively I can either find r minus 1 vertices here such that they are all connected to each other with red edges, and then all of them are also connected to vertex number 1 with the red edge, so now I have r vertices overall. Or I can just find B vertices here such that they are connected to each other only with blue edges. And that's all I wanted here. So I wanted either R vertices with red edges or B vertices with blue edges. Similarly, I can say the same thing about this side. So if the number of vertices that I have here is greater than or equal to n2, then I either find B minus 1 vertices here such that they're all connected to each other with blue edges, and then I say I add vertex 1, which is also connected with the blue edge, all of them, and then I get B vertices that are only connected with blue edges. Or I just directly find R vertices here such that they're connected to each other with red edges. So the only case that this kind of construction would not work is if I have less than n1 vertices here, and if I have less than n2 vertices here. And since I also have one vertex here, this means that the maximum number of vertices I can have for this construction not to work is n1 plus n2 minus 1. Right? I can have n1 minus 1 here, n2 minus 1 here, but I also have plus this one. So if I have n1 plus n2 vertices, this construction would definitely work. And this is the proof that the number of vertices that I need for parameters R and B is at most the number of vertices I need for R minus 1 and B plus the number of vertices for R and B minus 1. Now, from this, we can easily find a bound on our Ramsey numbers, because you can see that I'm taking the Ramsey number, I'm breaking it into two parts, and in each of these parts, either R is decreasing or B. So I can say that R plus B is definitely decreasing. So from that, I can conclude that the Ramsey number with parameters R and B is at most 2 to the power of r plus b times some constant. Okay? And the constant depends on Ramsey numbers for small values of r and b, and those are the things that you can compute by hand. Okay, so now I have an upper bound on my Ramsey numbers, and actually, because I don't like to have too many different values here, let's say that I just look at r of k. Okay, so I know that this is at most 2 to the power of 2k times some constant. So I have an upper bound on r of kk. I want to see if I can find the lower bound. And I want to use the probabilistic method to find the lower bound. So what does it mean if I say n, some number n, is less than r of kk? This means that if you give me a complete graph with n vertices, I should be able to color the edges red or blue so that I don't have a clique of size k that has the same color in all of its edges. Right? So every clique of size k in my graph should have at least 2 different colors. So let's try a probabilistic setting, and let's say that I just take every one of my edges, and randomly and with probability half, I color it red or blue. So I just flip a coin. If it was heads, I color my edge red, otherwise I color it blue. I want to see what is the probability that I get a clique of size k such that all the edges in this clique are of the same color. Okay? So let me erase this part. So we know that r of kk is at most 2 to the power of 2k, which is like 4 kk times c. Okay, so I'm just going to do what I'm always doing in this course, which is I define x to be the number of cliques of size k that have only one color. And then again, for every clique, or every subset of size k of my vertices, I can have an indicator variable. So let's say that S is a subset of my vertices, and the size of S is k. I just define an indicator variable xs, which tells me whether all the edges that appear between vertices of S have the same color or not. So x of s is 1 if every edge in my graph G, when limited to S, has the same color. And it's 0 others. So of course, as usual, I want to find the expected value of x. So I want to say that the expected value of x is just the sum of the expected value of the xs's. And so I have to find the expected value of every xs. Or in other words, for every set S of size k, I have to figure out what is the probability that this set, and that all the edges between vertices in this set have the same color. Okay? So let's find that probability now, which is the expected value of xs. Okay, so I have k vertices in S. These are my k vertices. Yes. And I have edges between every pair of them. But I want all of these edges to have the same color. So I have two choices. I can either color these edges blue, or I can color all of them red. Okay? So this probability is 2 divided by the total number of colorings that I can have, because all of the colorings have the same probability. So in how many ways can I color this? Well, the number of edges is just k choose 2, right? And for every edge, I can decide if it's going to be red or blue, so the number of colorings is 2 to the power of k choose 2. So this expected value is 2 divided by 2 to the power of k choose 2. Okay. Now, what is the expected value of x? The expected value of x is just the sum of the expected value of xs over every s that is a subset of our vertices and has size k. Okay? So, and this is at most, well, this part, I have a bound for it. So I just need a bound on the number of these sets. But
Why is it 2 to the power?
why is it 2 to the power of k choose 2 here? So I'm saying fix a set S of size k, right? And consider all the edges between vertices in this set. So I have k choose 2 edges. And so the number of different colorings that I can have is 2 to the power of k choose 2. Okay. Actually, this is exactly equal. So I have this expected value for xs, but how many different combinations of vertices can we choose so that they have exactly k vertices? Well, that's just n choose k. Right? So this is n choose k times 2 over power of k choose 2. Okay, now what do I want to show? I want to show that there is a coloring such that the number of clicks that have only one color is 0. Right? Because that's the opposite of the Ramsey number. So I want to show that this expected value is less than 1. Because if I can show that the expected value is less than 1, then there is a coloring in which the value of x is less than 1. And the value of x can only be an integer, so there is a coloring in which the value of x is 0. Okay? So I want this expected value to be less than 1. Okay? But to do that, I have to choose a value for n based on k. So I just want to choose a value for n such that this expression becomes less than 1. Since I forget how to do algebra, I'm going to just write this. So that expression is nk, n choose k, and this is 2. So k choose 2 is just k times k minus 1 divided by 2. Now, what is n choose k? N choose k is n factorial divided by n minus k factorial times k factorial. Right? So if I cancel these things together, up here I get n times n minus 1 times n minus 2, so on. I get k terms, and all of them are at most n. So I can say that n choose k is at most n to the power of k divided by k factorial. Right? So I do that replacement there, and what do I have here? Well, let me actually write it as a single fraction. Okay, so down here I have 2 to the power of k squared divided by 2, and I have minus k divided by 2, so I just put it up there. So let's say this is times 2 times 2 to the power of. Okay. Now I want to take some of these things that have the power of k out. So let's say I take this term and this term out. So I can say that this is at most n over 2 to the power of k divided by 2 to the power of k times whatever remains there. So I have 2 power of 1 plus k over 2, and down here I have k factorial. Okay, so this was just some small algebraic manipulation. Now, what do I have here? I want this whole thing to be less than 1. But this second fraction here is already less than 1 for any non-trivial value of k. Right? Because k factorial grows much faster than 2 to the power of k over 2. So I think even if you give it small values, you will see that maybe for 2 or 3, this is already less than 1. So it's enough to ensure that this part is less than 1. And to ensure that this part is less than 1, it's enough to have that n is less than 2 to the power of k divided by 2. Okay? So I can just say this thing holds, this holds, if n is less than 2 to the power of k, even if it's equal. Okay, but what does this tell me? This tells me that if I choose some graph with n vertices, if I choose an n and then create the complete graph on n vertices, and if my n is at most 2 to the power of k divided by 2, then basically all of this thing goes through. So I compute the expected value of the number of cliques of size k that have only one color, and that expected value would be less than 1. And since that expected value is less than 1, there should be a coloring in which the actual value of x is less than 1. So there is a way to color this graph so that you don't have a clique of size k that is entirely red or entirely blue. So by definition, this means that the Ramsey number with parameters k and k is going to be more than 2 to the power of k. Okay. So we found 2 bounds on the Ramsey number. Both of them show that it's exponential in terms of k, but the bounds are not really close to each other. Okay. So this was the last example that I wanted to give you about the probabilistic method. And now I'm going to switch to a completely different topic. So up until this point, what we did in terms of randomized algorithms was that I just gave you a lot of different techniques. We are now going to actually use them for some applications and actually create data structures and algorithms that use these techniques. So we know, for example, about the probabilistic method, we know about the Chernoff bounds, and so on. We're going to use all of them. Okay, so for today I'm going to start with 2 really basic data structures, and the first data structure I want to talk about is a tree, which, as its name suggests, is just a combination of a tree, a binary search tree, and a heap. Now I want you to recall our very first sessions in this course when we were talking about splay trees. The whole idea was that you have binary search trees that are balanced. For example, you have AVL trees and red-black trees and so on. But you're spending a lot of time and effort in balancing them. So it was both hard to code and also not very efficient in practice. So we came up with this concept of splay trees, which had a much simpler rule for balancing. This was basically this plain rule. Whenever you accessed an element, you would take it and rotate it all the way until it became the root. And then we said that this doesn't really prove the average runtime is O log n, or that the worst case runtime of every operation is O log n, but we had an amortized runtime of O log n. So now the idea in Treap is that I want to use randomization, and then I want to say that the average runtime is going to be O log n. Okay? So, what's a Treap? In normal binary search trees, we usually have a bunch of elements, and each element has a key. And then we create our binary search tree based on the keys that we have on our elements. In a Treap, every element has two different keys, let's say, or maybe let's call one of them a key and one of them a priority. So I have a bunch of elements, let's say E1, E2, En. So these are my elements. And each EI has two parts. It has a key part, let's call it Ki, and it also has a priority part, let's call it Pi. Now I want to create a binary tree, and I want my binary tree to be a binary search tree based on the keys Ki, so that I can do searching for the keys and search and application and so on. But at the same time, I want the same tree to also be a heap based on the priorities Pi. Okay? So let me give you an example. So let's say that I have a bunch of elements. And okay, just to make things simpler, I'm going to assume that all the keys and priorities are distinct. So we don't have repeated keys or repeated priorities. So let's say my elements are 2, 5, 6, 1, 8, 9, and 1, 7. Okay. So the first part is always the key, and the second part is the priority. Okay. So I want to create a tree and put each one of these elements in one of the nodes of that tree. But I want my tree to be, let's say, a max heap based on the priorities. Right? So the root of the tree should have the largest priority. So what is the largest priority here? It's this one. So the root of my tree would be 8, 9. So the key is 8, the priority is 9. But I also want my tree to be a binary search tree in terms of the keys. So now I know which elements should go to the left and which elements should go to the right. The elements that have a key that is smaller than 8 should go to the left. And the elements that have a key that is larger than 8 should go to the right. But here, if you look, well, all of our elements, maybe I should add one more, so then we have 10, 0. Okay, so all of these elements, other than 10, 0, have a key that is smaller than 8. So all of these elements will go to the left side, and 10, 0 will go to the right side. So I will have this thing here. And now on the left, I have to again talk about the heap property. So who's going to be the root of this subtree? The element that has the largest possible priority. So among all of these elements, this one has the largest priority, so it becomes root. Right? And now I have 2, 5, and 6, 1. But again, I have to look at, let me change this one. So I have 0, 5, and 6, 1, but I know that here I have to have a binary search tree based on the keys. So 0, 5 should go to the left of 1, 7, and 6, 1 should go to the right. Okay. So I will get 0, 5 here, and 6, 1. Okay, now if you look at this tree, and if you look at the first coordinate of every node, so if you look at the keys, it's giving you a binary search tree. This has key 8, and the keys here are larger, the keys here are small. And the same thing happens here. This has key 1, the key here is larger, the key here is small. But if you look at the second coordinate, which are the priorities, then this gives you a max heap. So the priority at every node is larger than all of its descendants. Okay? But actually, this informal algorithm that I used here to create this tree also shows us something else. So I can maybe call it a lemma. And the lemma is that for every set of elements, let's call it E1, E2 to En, such that no two elements have the same priority and no two elements have the same keys. So distinct keys and priorities. There is a unique tree. So, and the proof of this lemma is basically the algorithm that I did on this example, right? So if I give you a bunch of keys and a bunch of priorities, there is only a unique tree that you can create, again, assuming that the keys and priorities are distinct. Now, why is that? Just consider the algorithm that we had here. So, which element can be the root of the tree? The element that has the highest priority. But as soon as you fix the root, then you can say, okay, my tree should be a binary search tree based on the keys. So all the elements that have smaller keys will go to the left, all the elements that have larger keys will go to the right. So when you fix the root, the division between left and right is unique. But then you can continue the same thing. You can say on the left side, I have a unique root, and then I have a unique division, and so on. So inductively, you can say that you have a unique tree for every possible unit. Okay. So this is what a tree is. But how can we insert elements into a tree? Or how can we remove elements from a tree? Actually, I'm going to talk about a simpler operation first, and then I'm going to use it in all of these cases. So, if I just give you one node of your tree, and I ask you to change the priority, how would you do that? So, I want to have a change priority operation. So, for example, let's say I take this node, and I tell you that the priority was 5, I now want to increase the priority, maybe to 12, or I want to decrease it, maybe to 0. Okay? And let's not care about the distinctness. Let's say that I do it in a way that all the priorities remain distinct. How would you perform such an operation? So, as an example, let's take this 0, 5, and let's say that I want to increase the priority from 5 to 8. So increasing the priority doesn't really affect the keys. So the tree still remains a binary search tree on keys. So I just have to make sure that I get back my heap property on the priorities. Right? But to do that, I have to be able to somehow get this node here and move it up the tree, because now it has a priority that is higher than its parent. Right? But I have to move it up in a way that also preserves the binary search tree property. But we've already seen that we can do this with rotations. Right? So if I just rotate over this edge, then what I get would be something like this. So let me just draw it here. I have 8, 9, and I have 10, 0, and nothing changes here. But here I did a rotation. So 0, 8 comes up here, and now I have 1, 7 down here, and I have 6, 1 here. And now if you look at this one here, it satisfies both the BST, binary search tree property, and the heap property. Okay? So in general, whenever I have a violation of the heap property, whenever I have changed my priorities, and then I have a node that is larger than its parent, has a larger priority than its parent, I just do a rotation on that node and its parent. And the rotation is guaranteed to keep the binary search tree properties, so I'm sure that my tree remains a binary search tree on keys. But in terms of priorities, it basically moves the parent down and moves the current node up. So it's helping with preserving the heap property. I can maybe give you also like a more general picture here. So let's say that I have this node and I have its parent. So let's say the parent was A, this node was B, and maybe there's a C here, there's maybe a D here, and an E here. So I'm just doing the rotation like this. Right? So this converts my graph, my tree, to this case. I will have D here, and then A becomes the right child of B, and then I have D, E, and C, but I just add them in the same order as before. Now, previously, if you look at the keys, the order was D, B, E, A, C, and now again, if you look at the keys, it's D, B, E, A, C. So the ordering of the keys has not changed. But what happens with the priorities? Well, let's just look at that. Let's consider this graph and let's just consider the priorities. So what did I know before? I knew that the only violation of the heap property was between B and A. So this edge was the only place where a child had a priority that was larger than its parent. Okay? So in other words, D, E, and C all have priorities that are smaller than A. Okay? So I can put E and C below A here. That's fine. I'm also putting D as a child of B. But that's also okay, because D had a priority that was less than A, and B had a priority that was larger than A. So D's priority is less than B's priority, so I can do this as well. Okay? So when I do an operation like this, I make sure that the BST property is preserved and the heap property is also created here. But of course, a problem I might have is that I might need to move this B even higher. So this A here can have another parent, and that one becomes the parent of B, and it might be that B's priority is even larger than its new parent. But if that's the case, I just continue my rotations, and in the worst case, B will go all the way up until it becomes root. Right? So I'm guaranteed that I can just do these rotations, and I can satisfy all the properties of the tree. Now, how much time does this take? Yeah, it depends on the height of the tree, right? Or if we want to be even more specific, it depends on the number of ancestors that this node B had at the beginning, so the depth of B. Because I'm taking B and I'm just moving it. Okay, but what happens if I do the opposite? What happens if I want to change priorities? So I just take one node. Let's say I take this node and I say I want to decrease the priority. So I want to take this one 7 and maybe instead of priority 7, I want to give it priority -1. Okay. Again, the situation is very similar. I know that my binary search tree properties are still satisfied. So I just have to take this node and somehow move it down. But how do I want to move it down? I want to satisfy the heap property. So that tells me which one of its children should come up here, right? So this child has priority 5, this child has priority 1. So this is the child that has to come up and become the root here, right? So I just do a rotation on the edge between this child and the original vertex. So I just, sorry, I take it and rotate it. So, yeah, it's again the same idea as before. We're doing rotations, all the proofs are the same. We're taking this element and just moving it down. And we move it down until either all the properties that we want are satisfied, or it just becomes a leaf, and at the point where it becomes a leaf, again, it doesn't have any children, so it cannot violate any of the leaf properties. Okay? So, again, the runtime here would be bounded by, the number of rotations here would be bounded by the height of the tree. And if I want to, again, be very specific, I can say that I can just trace the paths here and go all the way and see where the final leaf is, and then my runtime is bounded by the depth of that final leaf. Okay. So, my point here is that in any case, your runtime is bounded by the number of ancestors of some node in your tree. And that node might change, but your runtime is always bounded. Okay, so now that I know how to change priorities, how could I add a new element? So if I give you some, let's say n plus first element, so I give you the key, and I also give you the priority. How would you add it to your tree? So the nice thing is that we know how to change the priority. So we can initially just ignore the priority and add it to the tree as if this is just a binary search tree. And after we added it as if it was just a binary search tree, then we change the priority and then we do all the operations that we did. So let me see. Let's say I want to add 7 and 4. Okay. So first I ignore the priority, I only take the key. So the key is less than 8, so it has to go to the left subtree. The key is larger than 4, so it has to go right. The key is larger than 6, so it has to go right. So it has to be added here. And then here I will have 7, 4. But, okay, this is saying that I ignored the priority is kind of the same as saying I'm giving it a priority of -infinity, right? Because I'm just allowing it to be a leaf. So let's say that what I have here is 7 and -infinity. And now after I have this, I take it and I change the priority to 4. So I get my 7, 4 back. And now again, I have to do rotations, right? So the priority here is 4, the priority here is 1. So I have to rotate it like this. So I would get 7, 4 here, and I'll get 6, 1. Okay, and now it satisfies all of my requirements. Okay, so adding was easy. Adding was that we just ignore the priority or put minus infinity as the priority. We add it in the binary search tree, and then we change the priority to whatever we wanted to. How about removing an element? So what happens if I give you some key and some priority and I tell you to remove it? Well, to remove the element, of course, you have to first find it. Right? But how would you find it? Well, this is a binary search tree. So you can just use the find algorithm in the binary search tree to find this particular key. So let's say I tell you to remove 1, 7. You first just ignore the priority and search for 1 in the binary search tree, you find it. Okay, but now I want to remove this. But it's not so easy. If I just remove it, my tree will get disconnected. It would have been much easier if this node that I wanted to remove was already a leaf. Because if it's a leaf, I can just simply remove it and I don't have to change anything. So after I find this node, I try to make it into a leaf. How can I make this node into a leaf? I can just change its priority to minus infinity. So if it has very low priority, it has priority that is smaller than everyone else, it will just be rotated down until it becomes a leaf. Right? So this is my algorithm for remove. If I want to remove this node, I would first change its priority to minus infinity, then it becomes a leaf, then I just disconnect that leaf and release it. So in any case, for adding or removing, all I'm doing is that I'm doing one change priority operation. Right? And everything else I'm doing is basically constant time. So I want to find the bound at the runtime of this change priority, which means that I like to have shallow trees again. Right, so I want to have a tree that has small bounds. Okay. But these were just the definitions of operations on these trees. But how do we use trees in practice? So in practice, you usually just want the binary search tree part of it, right? So you just want to be able to have a set of elements, you want to be able to insert new elements, remove elements, ask if an element is there, maybe find the successor, predecessor, all the things that you do with binary search trees. So the way we use a tree is that we just use random numbers as the priorities. Okay? So if you just give me a bunch of numbers and you want me to create a binary search tree on these numbers, instead what I do is I first generate a random priority for each one of the numbers, and then I create the unique tree for those numbers and those priorities. Okay? Now, how do I generate these random numbers? Let's say that I just take a uniform real number between 0 and 1. Okay? But in practice, you can also do with integers. As long as you make sure that some properties are going to be satisfied, and we will see it in the actual analysis of this. So for now, I just want to say that my input is a bunch of keys. And actually, let's say that I can also do some operations. So I can add, I can remove, or in the more general case, I can just do change priority. So I have a bunch of keys in my input, and I just want to create a binary search tree. So the randomization part is that for each key ki, I just sample some priority pi, and I sample it uniformly at random from segment 0 to 1. Okay? And so a minor detail here is that for this Treap to be unique, we needed to have distinct keys and distinct priorities. But if you sample it uniformly from a continuous distribution, the probability that you have clashes is basically 0. So it's fine. We can assume that even though we randomly generated this, we have distinct priorities. Okay. So let's find a bound on the height of this tree now. I can talk about the height of my tree because my tree is unique. And let's say that I have one of these elements, and just for the sake of analysis, let's say that I have these elements in sorted order based on their keys. Okay, so just for the analysis, I'm going to assume that K1 is less than K2, so on, less than K. It doesn't mean that my input was actually given in this order, so my input can be given in any order. Okay, so this basically means that EI is the element with the I smallest key. Now remember that when I was talking about these runtimes, I was saying that the number of rotations I have to do is at most the number of ancestors of a given node, right? Or at most the depths of a node. So let's try to find that. So let's say that xi is just the number of ancestors of ei. Or equivalently, it's just the depth of it. Okay, now I want to again write xi as a sum of indicator variables. So I can just define an indicator variable xij, which is 1 if ej is an ancestor of ei. And 0 on this. Now, of course, I want the expected value of xi. So I want the expected value of every xij. So for every two elements I and j, I just want to know what is the probability that j happens to be an ancestor of i. So the expected value of xij is just the probability that ej is an ancestor of ei. Now here I want you to remember when we were doing the analysis for quick select and quick sort, right? So what were we doing in quick sort, for example? We were just taking a pivot each time, and then we were dividing our elements into those that were smaller than the pivot and those that were larger than the pivot. But if you think about our algorithm for finding the unique tree, that's again what we're doing. We are taking a root, and we're taking this root based on priority. It's the node with the highest priority. But then we're using it as a pivot on the keys. Right? So we're saying that all the elements that have smaller key should go to the left, all the elements that have a larger key should go to the right. So I can now do an analysis that is kind of similar to the analysis that I had for quicksort. I want to know what is the probability that Ej is an ancestor of Ei. I say just look at all these elements, Ei plus 1, all the way to Ej. I'm just assuming that J is larger than I, but it would work even if J is smaller than I. Okay? So just look at all of these elements. And again, forget about the priorities, just focus on the keys. When would Ej become a parent of Ei? This would only happen if Ej is chosen as a pivot, because our pivots are the roots basically. And then all of these elements go to the left of Ej. Right? But it wouldn't work if any of the other elements is chosen as a pivot first. So if any of these internal elements, if any of them other than Ej is chosen as a pivot first, then Ei would go to the left of the pivot, Ej would go to the right of the pivot, and then Ej would never become an ancestor of Ei. Okay? So, but now let's go back and think again about how we chose our pivots. Whenever we wanted to choose a pivot, we always chose the element with the highest priority. So if I want here I want Ej to be the first pivot, then Ej should have a priority that is higher than all of these elements between Ei to Ej minus 1. So not only its key is larger, but also its priority has to be larger. Okay, so this is at most the probability that Pj, so this is priority of J, is larger than the maximum of, or actually let me just say it's the maximum of Pk, where k goes from I to J. Okay, so the maximum priority in this whole segment is the last one. Okay, but we chose the priorities randomly. So what is the probability that this particular element gets a priority that is larger than all of the others? Well, it's just going to be 1 over j minus I plus 1. Right? Because each one of these elements had a randomly chosen priority. So each one of these elements has the same probability of being the maximum. And I want the probability that this particular element is the maximum. So that is at most 1 over j minus I plus 1. Okay. So this is most 1 over j minus I plus 1. And I mean, this was the case where j was larger than I. Of course, I can also take the case where j is smaller than I if I have a picture like this. So I have Ej plus 1 all the way to Ei. And again, I want this one to have the maximum probability, the maximum priority. So again, the thing is the same, so I can just add absolute value there. So the expected value of xij is at most 1 over the absolute value of j minus I plus 1. Okay. So now that I have that, let's find the expected value of xi. So what is the expected value of xi? And remember, this is basically our runtime. It's a bound on our runtime, right? Because the expected value of xi is the number of ancestors of this element, and I was taking this element and just rotating it up. So the number of rotations would be at most the number of ancestors. Okay. It's just the sum over every j that goes from 1 to n, but it's not the same as I, of 1 over j minus I plus 1. So I can just break this down into two parts for j's that are smaller than I and j's that are larger than I. So this is the sum of all j that is smaller than I of 1 over I minus j plus 1 plus the sum of all j that is larger than I of 1 over j minus I. But in any case, I have different values here, but all of these values are between 1 and n. Right? So this is less than or equal to twice the sum of 1 over k, where k goes from 1 to n. Right? Because this is less than the sum of all 1 over k's, and this is also less than the sum of all 1 over k's. And yeah, this is in all log n. Right? Because again, the idea here is that this is the harmonic sum, and you can approximate the sum by the integral, and the integral of 1 over x is just the natural log of x. So this is all log. So this shows that all of our operations in this tree are going to have an expected runtime of O log n. So the difference between Treap and display tree is that in display tree we didn't have an expected runtime, there we just had an amortized runtime. But here we have an expected runtime that is O log n. Okay. So I'm now going to give you another data structure which basically solves the same problem, but with a different idea, but also with randomization. And it can actually prove that all of these operations will be done in O log n with high probability. So this is the skip list. Imagine that you have a linked list, and imagine that this linked list is sorted. Okay? So I have a bunch of items. Let's just give them some values. So this is maybe 2. So let's say I have a linked list. Let's say the elements in my linked list are sorted. And let's say I also add a starting element, which is just minus infinity. And let's say I add an element at the end, which is just plus infinity. If I give you a linked list like this, insertion is fast, right? So if I tell you to add, for example, 7 after 6, that's just constant time. But even though it's sorted, searching is not fast, because you can't just access, let's say, the ice element here, right? So if you want to search for an element, you have to start from the beginning or maybe the end, and you have to traverse this whole thing until you get to your desired element, or until you get to something that is larger, and then you know that the element doesn't exist. Okay? So what happens if I want to do the same operations that I was doing in a binary search tree? Now, searching is expensive, deleting is not expensive, and inserting is also not expensive, assuming that you don't need to do a search. So let's see how we can make our search a bit faster. So I'm starting from here, and every time I'm going forward by one step. What happens if every time I go forward by 2 steps? So maybe I can have another layer of linked list on top of this, so that I only have half of my elements. So I have 2, I have 6, I have this one, which is 100, I have this one, which is 1001, and I will always add my minus infinity and plus infinity as well. Okay? And so let's say I created this linked list. This is also sorted, but it only contains half of the elements in the previous one. So I have linked list like this. And let's say that I also have pointers between the 2 lists. So I can switch between these 2 lists to the same element whenever I want. Now, if I do this, then searching can be made a little bit faster, right? Because now if I want to find, for example, 8, I start at the top here, and I go as long as I have numbers that are smaller than it. So I go all the way to 6, but I don't go to 100 because that's larger. And then as soon as that happens, I go down a level, and then continue my search in the main linked list. So in a way, this second layer is just giving me some shortcuts so that when I'm going from, let's say, 2 to 6, I don't have to see 5. I can just jump over it. It's a faster way of traversing this. But of course, this is not fast enough, right? Because this just gives me a factor of 2 in my runtime. So it just decreases my runtime by half. But what happens if I just continue this? So what happens if I add another layer? I add another layer here. So let's say I take the 6, I don't take the 100, and let's say I take the 1000. Okay. Now, again, I have minus infinity here. I have all these edges. I have pointers like this. And I have plus infinity. Okay, and let's even add one more layer. Let's add another layer that also has like half of the elements. Again, here I can choose the 6, or I could choose that one, but it doesn't matter. Okay, in general, if I have n elements, I can have log n different sorted linked lists, and each level is going to have half as many elements as the level below it, right? And now if I want to do a search, I can start at the top level. I just go through the top level as much as I need. Then as soon as I get to an element that is larger than what I'm searching for, so let's say I'm searching for 1000 now. I go here, 6 is smaller, but plus infinity is larger. So now I go down, and I go to 1001, this is also larger, so I come down again, I go to 100, I see that 1001 is larger, so I come down again, and I go right, and I find 1000. Okay? So this is how I can do the search. Now, how much time does this search take? This search will take me log n time, right? Because I have log n different levels here, log n different linked lists, and in every linked list, I'm taking at most one step to the right. Because if at some point here, let's say, if I had to take 2 steps to the right, then I could just take those 2 steps as one step in the higher level. But my algorithm doesn't do that. My algorithm goes to the right as much as possible in the higher level before coming down to the lower level. So I'm sure that at every one of these levels, I'm going to the right at most once. So my search time is now log n. But this thing was assuming that we have a static array. It was assuming that all the numbers were given to us at the beginning. what happens if I want to also support insertion and deletion? So what happens if I say I want to be able to, for example, add 7? Suddenly the whole system collapses, right? Because if I want to add 7 here, then here I should have 8, not 100, and so on, and then I have to rebuild all the levels into it. So here's the idea that helps us. We can just do randomization. Instead of saying that I want exactly half of the elements here, and I want exactly the elements that are, let's say, at an odd position to come up here, I just say that I randomly pick half of the elements of this list and add it here. And then I randomly pick half of the elements of here and I add it to the next level, and so on. But let me be more specific about it. So how do I add? Well, we have several operations, right? So we have the search operation, and we saw that that one took O log n. But I have to come back and analyze it again now that I'm adding the randomness. So without the randomness, it took O log n. But now if I want to add an element, of course, first I have to find where I should add it, right? So first I do a search. And that search tells me where I should add my element. So let's say I want to add 101. So I do a search for 101, and it goes something like this, and I figure out that this is the place where I should add 101. Okay? So now I just add it to the lowest level. So I just add it like this. And I erase the previous ones. So my lowest level linked list is now correct. Right? But in order to decide whether I want to add it to the next level, I just flip a coin. And with probability half, I add this element in this next level as well. And if I added it in this level, then I continue. I again flip a coin, and with probability half, I add it to the next level. And so on. So I basically take a coin, I just flip it as long as it comes heads, and I just keep adding this element to new levels until my coin comes up tails, and then I stop adding. Okay? So, how much time do I spend for adding an element? My worst case is infinite, right? My worst case is that I just flip this coin and it comes heads forever, and I'm just adding more and more layers forever. Right? But what is the expected time? So I definitely add it in the first level down here. But the probability that I add it in the second level is just a half, because I'm flipping a coin. The probability that I add it in the third level is 1/4, because I'm flipping 2 coins and both of them should come heads. And then 1/8 and so on. So the probability that I add it to the case level is 1/2 to the power of k. And so the total number of times that I add it is not going to be too much. But this would basically be constant, right? So add is just O1, but plus the time I need for search. Right? Okay. So now the question is, how much time does it take for me to do a search? Now previously, because this whole system was created in a very nice way and it wasn't randomized at all, I would say that at every level I'm taking at most one step. So I could say that my search takes log n time. But now you don't have this nice property anymore, and everything is random. Okay? So you have to think about the expected number of steps in your search. Okay. To find that, let's first find a bound on the number of levels that we have. Because if I'm doing a search, I'm always starting at the top level and I'm always ending in the bottom level, right? And now with this randomized idea that I had, it's no longer guaranteed that I have log n levels, right? Because the worst case was that I just get heads over and over again and I will have a lot of levels. Of course, in practice, when you implement this, you can just put a bound and say don't add after the 100th level or whatever, or the log nth level. But in theory, we don't have that bound. So the first thing I want to prove is that the number of levels is going to be small with very high probability. So I want to say this is my theorem or lemma. I want to say with high probability the number of levels, the number of different linguists that I have, is at most some c times log n. Okay. So since I want to prove this with high probability, basically I want to find a bound on the probability that the number of levels is more than this c log n. So what is the probability that the number of levels is more than c log n? Okay. When will I have more than some number of levels? When in one of my additions, I get at least these many heads, and I just add this element in all of these levels, right? So this is basically the probability that there is an element such that when I added it to my list, so I'm assuming that I started with an empty list and added everything with our addition here. So this is the probability that there is an element such that when I added it to the list, I got at least c log n heads when I was generating the randomness for that element. Okay, so I have n elements, so I can say this is at most n times the probability that when adding element I had c log n heads. Probability of having c log n heads. Now, I just have a fair coin, right? So probability of having c log n heads is just 1 over 2 to the power of c log n. Okay, 2 to the power of log n is just c. So this is n. Sorry, 2 to the power of log n is n. So this is n times 1 over nc, right? Which is just 1 over n to the power of c minus 1. So now we can choose whatever value we want for c. Let's say that I want to let my number of levels to go up to 10 log n. I just set c to be 10, and I say that the probability that I would ever have more than 10 log n levels is at most 1 over n to the power of 9. And that tends to 0 really fast when the number of elements n is growing, right? So in practice, honestly, we will always just have log n levels and not more. So if you code this, you can just have an if in your code, and if you have more than log n levels, you don't continue. You don't add the elements anymore. But this is like a nice theorem that shows that you don't necessarily even need to do that. Like with very high probability, the number of levels is one. Okay. Now I know that with high probability, I have few levels, but this doesn't mean that my search is going to be fast, right? Because when I'm doing a search, I'm not only moving between levels, I'm also moving in a single level. So it might be that in a particular level, I have to go a very long way. I want to show that that's also not really possible. And I want to show that with high probability, that's not going to happen. Okay. Now here's the thing. I want you to consider a particular search. So let me just erase this one and let's go back to the original setting here. So let's say I was searching for 1,000. What is the path that I will take in this whole data structure? So I start from here, and I go down here, right here, down here, and right here. That's how I found 1,000. So now I want you to think of search in reverse order, backwards. So instead of thinking of this path, just think of this path that goes in the reverse order. Okay? Of course, they both have the same length, so I just want to find the bound on the length of these paths. Okay, so I start from this 1,000, and every time, what do? If I have an edge to go up, I will just go up. Otherwise, I will go left. And I continue this until I get to this minus infinity on my top list. Now, I want to find the bound on the number of steps that I take. Let's say at some point I am somewhere in my data structure. What is the probability that I go left, and what is the probability that I go up? So if I'm at this point, if I can go up, I will go up. So when this element was added, if the first coin flip gave me heads, and I had also added this element to the next level, then now that I'm searching backwards, when I get here, I will go up. So the probability that I go up is basically the probability that the first coin flip when I inserted this element was heads, which is just a half. And you can do the same argument at every level here. So at every step, I'm going up with probability a half, and I'm going left with probability a half. Right? Now, here's the thing. I have this theorem, which tells me that I can go up only C log n steps with high probability. Right? So if I can go up only C log n steps, the idea is that I'm roughly taking the same number of steps up and to the left. So my total number of steps should be at most 2 C log n. Okay, that's what I intuitively think. But now we have to formalize this. So let me just erase this theorem. So the number of levels is at most C log n with probability 1 minus 1 over n to the power of C minus 1. So I can erase this one. Okay. So here's the part where we're going to use everything from before. So I want the expected number of steps in my search. So the expected number of steps. Okay. And this is basically the expected number of steps that go up. So I'm just going to write it like this. Plus the expected number of steps that go to the left. But I know that with high probability, the expected number of steps that go up is at most C log n. Okay. So here's what I want you to think about. Let's say that for every one of these insertions, we flipped C log n coins. Or, no, okay, let's say for, okay, for every one of these insertions, let's say we flipped a lot of coins. So whenever my coin comes up heads, I'm going up. Whenever it comes tails, I'm going left. So I have a sequence of coin flips, and that basically gives me my paths. So what do I want to bound? I want to bound the probability that the number of steps to the left is more than some number. Okay? let's say that I want the probability that the number of steps to the left is more than 5 times this, more than 5 times the number of steps, or more than 4 times the number of steps that I had going on. Okay? Again, every time I'm just flipping a coin and with probability half deciding to go left or right. So this is the same probability that we were computing in previous sessions. Remember, so we had this thing, we were computing the probability that when we just flip n coins, the number of heads is more than 80% of the number of coin flips. Right? And in the previous sessions, we saw a lot of different bounds for this. We saw that Markov says this is at most 0.625, and Chebyshev said that this probability is at most 2.78 divided by n, and Chernoff actually said it's 0.859 to the power of n over 2. Okay? So the only difference here is that instead of throwing n coins, instead of flipping n coins, I'm flipping 5 times c times log n coins. And I want to see what is the probability that 80% of them come tails, so that I go left. Right? So this probability is at most, let's use the Chernoff bond here, 0.859 to the power of, well, our n is now 5c log n divided by 2. Okay? And this probability also tends to 0. Right? So, what did I prove? I proved that with high probability, the number of levels is at most c log n, and assuming that the number of levels is at most c log n, with high probability, the total number of steps that I take is at most 5c log n. Because I take c log n steps up and 4c log n steps to the left at most. So just combining these two, with high probability, I can say that my search takes O log n time with high probability. Because c and 5 are just constants. Right? And my addition took constant time plus the time for search. So this is also O log n with high probability. Okay, so that's it for this session, and in the next session we will see some more randomized algorithms.